So some of the influence from vegetation, apart from the ones I already said, like how vegetation was dependent on all of those other things, or the influence in vegetation in this case, are going to be the following. So as we said before, vegetation itself can be either a driving force or a resisting force. And the way that it can be a driving force is that it's going to add weight to the slopes, as we're seeing here on the bottom picture. And the way that it can be a resisting force is by adding strength and cohesion to the slope materials by the roots of the vegetation itself, right? Another thing that it can do is slow that surface erosion by actually being planted there. All those roots are going to slow that surface erosion, and they're also going to provide a lot of conduits for water to flow through, to permeate, okay? I have said before, and I think I've strengthened this point a lot, is that water is going to be one of the main influences on slope failure. So how this water is going to influence directly, and I'll explain that a little bit more, is that it will increase the soil weight and the pore pressure. So as you're seeing in this image right here, each of these granules, each of these grains is one singular soil particle, if you would, one grain. Usually in an unconsolidated soil, or even in a consolidated soil where they are cemented, there may still be some pore space, some empty space between the grains. So this empty space between the grains is where water will flow through. It's going to be that or the connection between each of these pore spaces is going to be the main factor to give a soil permeability or not. So say if this pore is not connected at all to this one, so there's no way that the water will flow through, then it is impermeable overall. However, if there is a chance for these grains to move, for example, and then water shift from this pore to this pore, then it's more permeable. Okay. And so many a times when water does infiltrate into the soils, it will occupy those empty spaces, or what used to be empty spaces, and are now full of water. And that is when we call a soil to be saturated. Okay? So by saturating that soil by the water, occupying those empty spaces, you are going to get added weight. That water is heavy. So you're going to get added weight to the soil and hence to the slope overall. So as we said before, the main driving force for mass wasting events is going to be the weight of the slope, right? So if you add the weight through water, then you're just simply increasing the driving forces. Okay? So all of these pictures and diagrams are just basically exemplifying that, and you're free to look at them on your own later. Okay. And so running along the same lines, water, can saturate a soil enough so that it can create mass wasting events or landslides after a storm occurs. If there's enough water within that soil, after the storm occurs, maybe the water kind of spreads throughout the slope, and that is when the landslide occurs. That could happen. Another way in which water can, destabilize stability, and that sounds funny, but how it can do so is it can erode the basis of these slides or slumps or flows by, taking down the toe. So as we're seeing here in this example, this used to be a nice lump. So the water eroded the nice lump, and now because it took out that toe that was in its own kind of stabilizing the slope, the fall, then it's increasing the instability. So let me kind of show that in a picture. So if this is my kind of slump, and this is going to be the toe of my slide, this is going to be all the stuff in between. If I were to, make water flow and be removed of this toe, then all of this material that sits on top doesn't have anything to sit on top of. So it's basically now you're basically increasing the driving force of driving it downwards by removing that toe. Hope that makes sense. But if not, let me know. So another aspect that might influence whether or not we get mass wasting events and which kind is going to be time. So the different forces, both the driving and the resisting forces, are going to change over time. Think of it on a seasonal perspective. So you're going to get a lot more moisture, say, in the spring than you're gonna get over the summer, over the late summer, for example, here in the Treasure Valley. So you're adding a driving force during the springtime, and you're decreasing that driving force during the late summertime. Another way in which you can have seasonal changes may be or resisting forces, I should say, may be the vegetation content. So if you have springtime where things are growing dramatically both above ground and below it, then you have more root systems that might hold better the soil itself, or you may be adding so much of that vegetation that you're adding to the driving forces of moving down slope, right? Another way in which these forces change seasonally is by the water table height. So that's going to be the groundwater height above or below, I should say below the ground surface. So if your water table is higher than some of the surface water that you're seeing, then it's very likely that the soils next to that surface water, meaning say a channel or a lake, so the soils is very likely that they are going to be oversaturated, and hence it is more likely for a mass wasting event to occur. You're adding to that driving force. So again, if your water table is very high, then it is likely then that soils are going to be oversaturated, and hence you're going to add to the driving forces, which will cause mass wasting events. Okay? If the water table is lower, then it is not as likely that soils, higher up are saturated. So you're not as likely to get mass wasting events. Another way in which time can influence whether or not you get mass wasting events is that with time you get certain chemical processes to occur. So don't get too scared about the chemical reaction itself, but what it says is that carbon dioxide, which again we have naturally in our atmosphere, but also because of the burning of fossil fuels as of late, carbon dioxide will react with water vapor up above, and then they will form carbonic acid. Carbonic acid, when it falls, is going to have a chemical reaction with calcite, with limestone type of rocks, type of material, and is basically going to dissolve the calcite into having the calcium ion separated from the carbonate part of it, I guess, or not carbonate part of it, but the carbon and oxygen part of it. So by doing so, you are basically eroding away any sort of place that used to have limestone in it by the use of carbonic acid. So this process wouldn't happen if time wasn't allowed to continue. If I simply took a snapshot of today, there would not be this chemical reaction occurring at one single second kind of thing. It's an ongoing process. But when you have this type of reaction where you disintegrate the limestone, you get environments kind of like caverns, as you're seeing down here. That is called karst topography, and in fact we're going to see that, I believe it's next week under that lecture, and one of your discussion boards is going to be about this. So you are going to get this type of environment where you are eroding away literally the underlying soil, and as you are eroding it away, all the overlying soil, say over here on top of this cavern, is going to become weakened and is going to be more likely to fall. It's got a lot more driving force now than before because there's no resisting volume of rock underneath. So this picture over here is in China, and all of this area is limestone, like the rock that gets eroded by the carbonic acid. And it is really cool to think about because what this environment used to look like, it used to be flat up here. This used to be the top, and because of so much chemical reactions, so many chemical reactions have taken place, all of the stuff in between the limestone started eroding away, and now you only see little towers, if you would, of what used to be. So knowing all of those influences on the amount of mass wasting events that we could have, the amount and also the type, it is easier for us to pinpoint geographically which areas are going to be more prone to mass wasting events. So anywhere that has slopes and mountainous regions pretty much is prone to that. So you see here in the western US, you got the Cascades over there, and you got the Rocky Mountains. You see all of that is fairly prone to that. And over here in the east, you got the Appalachians. So you see that anything that has slopes and mountains is already going to be prone to them. Also, we saw that things that have thick soils and a lot of vegetation could also be driving forces. So that could associate it with that. And also the amount of moisture that a certain region has is going to affect greatly. So that's partly why in the Appalachians you see just so much more, mass wasting hazard than you see, for example, in the Rockies, because it is a lot more moist than the Rockies. And so some of the things that may increase this activity is going to be the urbanization and development of those prone areas. So you already have prone areas, and now you are increasing the instability of them. You're cutting the trees and certain prone areas, so now you are debilitating those slopes. And then as we're changing our global climate patterns, maybe we're adding more CO2, which will in turn increase the amount of carbonic acid that will later on denudate or erode that limestone, will obviously also weaken our areas. And so some of the things that we as humans do to either increase or decrease landslides, in this case increase landslides, is going to be urbanization. So while we urbanize, we usually remove this anchoring vegetation, especially in these arid areas where the vegetation actually acts as a resisting force, not so much as a driving force. If we remove the vegetation, then our slopes become weakened. Another thing that we can do is road building. When we road build, we no longer let that slope have the permeability it needs to in order for water to flow through and not become stable in one specific area. And then we can build at higher elevations. We know that higher elevations tend to also have steeper slopes. And then lastly, we can do grading, which are benches cut for home sites like you see up here. So all of these I guess all of them actually happen at the Terra Nativa landslide over in Boise, over here as we're seeing. So what happened for these benches cut for home sites is what they do is that they take some of the soil from up here, and then that soil they put over here to make this whole kind of flat surface, kind of like a little terrace. And so both sides of it are now more prone to landslides, because this bottom one, this bottom one is now less consolidated, and so if it becomes saturated with water, it might give in. And this top one over here doesn't have anything to stop it right below, and so the driving forces can be much greater, and so it might also turn into a landslide.